And obviously email is always there for you to ask these questions. Tomorrow, once you have submitted the homework, you'll have the practice exam from last year and the conceptual questions. These are additional conceptual questions on top of all the questions we have discussed in the lecture. Okay. Any questions for homework 4 or exam 2 before we move on to the topic today? Anything that's confusing or would you like to discuss? All good? All right. All right. So basically, what we want to focus on today is finishing up the topic of inviscid flows, or sort of continuing the discussion. So in inviscid flow, last time we had discussed, this is when we think Reynolds number is infinity. Okay, which means that viscosity is going to 0, and if viscosity is going to 0, we had mentioned that there will be no shear stress, right? There will only be so there is no viscosity, is basically 0. So the governing equation that we have derived last time, and we had mentioned governing equation, and note that these are for steady and irrotational systems, steady and irrotational flows. We have derived this. Irrotational flows means that del cross V is 0. We have derived that there are two equations. Either we use del square phi is equal to 0 or del square psi is equal to 0. Either option is fine. Where for velocity, for psi, we look in table 612. Or for this case, we'll use velocity grad phi. Okay. So in the class, what I will do is I'll do a problem with this approach. Okay. In your homework, you use the grad phi approach. Okay. So you can see both approaches. Yeah. Any questions? Okay. And so yeah. Yeah. Sorry. Maybe I was not very good with writing. This is psi actually. And this one is phi, the first one. Okay. So phi and psi. So we can have the potential in case we have the velocity. So this is your homework. 4 problem 5 shows you this approach, and in the class we will do is the psi approach. Okay. And once you do this, find velocity, and then use Bernoulli's to find pressure. Okay. And Bernoulli's equation is P by rho plus V square by 2 plus GH is equal to constant, where V is Vx square plus Vy square plus Vz square is the magnitude. Okay. And what was the important part is that no slip cannot be applied. Okay? Don't forget that in inviscid flows, you cannot apply no slip. So any confusion about what we discussed last time before I go into an example problem? Anything that's confusing about this structure or this sort of equation set? Okay. So you start with Laplace equation. Yes, please.
I guess I'm not very clear what exactly
what phi is. Yeah, so it's a scalar function. So think of it like this, that if you take the gradient of the scalar function, you get a velocity, right? So it's not so physically there are meanings for this function. Basically, it helps you with flow visualization, and there is a property between stream function and the potential function as well. But we don't discuss that. It's just a little bit of more of details there. So people have used these functions to basically understand how the flow is happening.
Yeah, but like mathematically, how does that relate to psi?
Oh, mathematically. So there is a relationship, and I may be getting it wrong. Basically, I believe they're normal functions to each other. So if you sketch them out, there's some sort of normal property between them. But I don't myself remember what the property is. But you can see that. So I will try to show you. Actually, I'll try to address your question once I solve the example. This is how they will be different. Okay, so I will try to address that in a bit. But I can help you with that. We can talk about it. Any other questions here? All good. All right. So let's try to do an example now. So to make sure we are clear. So think of now a cylinder. Okay. In your homework, you have a sphere. It's a very simple, similar system. So a cylinder, let's imagine you have a cylinder and you have some fluid flowing over it with velocity u. Okay, so and the cylinder is obviously has this, it's like kind of in this direction, but we'll ignore axial dependence. So nothing along that, ignore axial dependence. So we are not thinking of any z dependence. We are essentially thinking of r. So this is y, this is x, and then r and theta. I believe you are familiar with this sort of part. Okay, so let's just sketch it again here to clarify. We're looking at a problem here at this plane only. Okay, r and so what is the goal? Okay, so the goal is the fluid will naturally flow over it. So the flow will come and go around it. But now there is no viscosity and so on. And what we want to find is velocity vector and pressure. Okay, and we have been given that pressure far away is 0. The pressure far away is 0. It's a reference pressure, so it's just 0. Some constant or 0. Easiest to use 0. So find velocity and pressure, and then find the drag. So force applied, then find the drag. And once you do that, find drag. Okay. So you can imagine this is very similar to what you are doing in a homework. Instead of a cylinder, you will have a sphere. Okay. So that's the only difference. And the flow is inviscid. So inviscid, steady, rotational. Inviscid, steady, rotational. This is a very simple problem, very instructive. I really like this example because it basically combines whatever you have been learning in this second part and kind of shows you how to think about this problem. All right. So there was a question, right? What is the relationship between phi and psi? So we have now an approach. We can use the psi approach or the phi approach. Okay. So let's say you say that I want to use the phi approach. Okay. Let me just try to kind of go there first. So let's say you have a choice. So you can use either the phi approach or del square psi is equal to 0. So you have two approaches. But now if I want to use the phi approach, and some of the students have definitely asked this question, we don't know how to think of this sort of velocity, how to define velocity. So I've just basically taken this snapshot from the book, is that basically these are just rectangular coordinates. You know what is the gradient, you know what is the gradient in the cylindrical coordinate, and you know what is the gradient in the spherical coordinate, right? So of a function f, you can just replace it with phi. And so grad of phi, let's say in the cylindrical coordinate, so you write it down. So I will write this down on my screen and then we can discuss it. So grad of phi, basic in the second column is del phi by del r er plus 1 by r. Yeah, I'll just give me 1 second because I also have to see the formula. Del phi by del z is z. All right, so here we go. So basically we have written this here, and all you need to say is, well, I will have, this is my VR, this is my V theta, right? And I cannot, there is no Z dependence. So just forget this because there is no Z dependence. So I have my VR and V theta defined now. Okay. Okay, does it make sense? Any questions here? Is it clear? All right. Alternatively, I have the second approach psi. Let me, my phi's and psi's often get. So don't forget to, let me know if it's confusing. So the second approach is psi. So how will you do the second approach is we don't have a definition, set definition. We have to look it up in the table. Because the whole idea of stream function, as you may recall from previous discussion, is that stream function automatically satisfies the continuity equation, which kind of, and Philippe had also derived the exact formula for psi. So with hope this is clear. So now let's look at the table. So table is this string function 6 table. So can anybody tell me which row should it choose? 1, 2, 3, 4. There are 4 cases. Which row is this one? The second one. Okay, so they know that there are two cylindrical ones, Z and R and theta. We are in the R and theta one. Okay, and if it was this R and Z one, then we will not use Laplace of psi. We'll use E square of psi is equal to 0. Right? We had discussed this last time. So then you will use this definition and then use E square of psi. But for this purpose, then you get the R and theta. Okay, so we'll use the del square of psi. So now VR, in this case, VR is, and I'm just typing it up from 1 by R del psi by del theta, and V theta is minus del psi by del R. Okay. So I hope this is clear. So now let's go back. So this is essentially what we have. So to answer to your question, as you can see, VR was del phi by del R, and here VR is 1 by R del psi by del theta. So as you can see, there is clearly some similarities because VR has to be the same, right? There is a similarity between the two functions. I think they are normal functions, but that's a detail I think that you probably won't need to use it. But people have used it. It's a principle people use in fluid mechanics. I'm just not as familiar with it. So for this in your homework you will do the same thing, but for spherical coordinates, and for spherical coordinates you will have the R and theta, VR and V theta. V phi is 0 in the case. Okay, so let me just explain to you what you will do in the homework. In the homework, basically you will use this one, and there is no phi because the problem says there is no phi dependence. It's just R and theta, so you just use these two and you make progress. So you have this. So my governing equation is clear. So this is my governing equation. This is a choice. You can go to the second approach and still get the same answer. So let's choose this. Choose this. And my first step is governing equation is clear. Now my second step is boundary condition. Okay. Boundary condition. So what do you think is the boundary condition at R equal to capital R? And let me just do a poll question here at the surface. So what do you think is the boundary condition we should apply at the surface? Take your time and take a look at the equations, and then what do you think are the equations you should apply at the surface? Solid cylinder. So solid cylinder in a liquid. Inviscid fluid could be a fluid also. All right, maybe another 15 seconds, just in case a few of you are trying to get your answers in. Yes. All right, maybe let's stop the poll now. Hopefully I don't forget. Okay, so there is some split, and I understand why students would also pick A, but remember this is Inviscid, so no slip does not apply, and that is a common boundary condition error that I've seen repeatedly. Whenever you have Inviscid, we can only apply no penetration, and that's why you only have B, we cannot apply no slip. So that was the idea, that you cannot apply no slip condition. You cannot apply no slip here, so it's just B. And so I will just write it down. Yeah. All right. So this is the idea, is that only no penetration, no slip doesn't apply. So no slip doesn't apply. All right. So we have this equation, and what I've done is basically, so remember that our governing equation is in terms of psi, right? Yes, no. Discuss. Oh, it's a psi. It's all our psi. Yes. Let me clarify. So d psi, del psi here. del psi by del theta is at r equal to r is 0. Why? Because VR is 0. So remember that our governing equation is in terms of psi, right? So, and my boundary condition I'm writing in VR, so it's just best to convert it into psi. This is what you do in your, homework 4 and problem 4 and problem 5 is that the boundary conditions in velocity, but we want to solve in terms of psi because that's just one way to. So that's why we just change it into the psi. Okay. Any questions on how I've done that? I've just taken the formula from the top and just replaced that, and you get del psi by del theta. Yes.
Why did you write it as like an integrated? Like like with
Yeah. So the point is that I'm writing it as because my governing equation is in terms of psi. So if I just leave it in terms of velocity, I cannot solve the governing equation. So that's why I've changed it. Okay. Any other questions? Okay. So now what is my other boundary? That's at infinity. At r equal to infinity. And what is the velocity at r equal to infinity? Would somebody suggest? How should I write it? What is my velocity at far away? U, but velocity also has a direction, so it's u ex, right? It's in the x direction. So it's u ex. And at this point, sorry, not v, just v vector, my mistake. V vector. And so at this point, again, don't forget that you don't have to do any trigonometry or any kind of transformation. Just look it up in the appendix, and you will be able to see this. So I'll just give you another poll question here: how to transform this, and the answer is very straightforward. But let's just do it, and is that you get the let's get the. So this is something you can look it up in the book. I think it's in table. It's in appendix A7. So whenever you're because you are trying to find things in terms of VR and V theta, you need to break EX in terms of ER and E theta, right? So you just look it up on the table. What's the formula? So I'll give another maybe 30 seconds. All right. So hopefully most of you did get it right. Basically, we should have both components because you need to have ER and E theta. So you just plug it in and you get the answer. Okay. Plug it in and you take the components, you get ER and E. So you have this as your ER and E theta. All right. Any questions here? Please let me know if there's any question. I'm going through this because I want to make sure you understand this, and this will reinforce all your creeping flow and other calculations as well. Just a process, okay? So boundary governing equation was in psi. We went to VR, and then we convert the now. This is not enough. I cannot still solve the problem because I need to convert this into psi, right? I cannot solve it otherwise. Governing equation is in psi, so I need boundary conditions in psi. All right. So let's go now. Next step. VR is what? 1 by r del psi by del theta. R going to infinity is u cos theta minus del psi by del r. It's all psi, by the way. Please don't get confused between psi and phi. All psi is minus u sine theta. And we get this as r going to infinity. This is our next problem. Any questions here? Anything that's confusing, not clear? Yes.
So every time what you get here is not going to be the same.
What do you mean?
So you have it in DR or it's U cosine theta.
all is going to be the same. Yeah. I have to basically, that is my VR, right? Yeah, it has to be consistent. Yeah. All right. So now what is the problem? I have governing equation del square psi, right? I have boundary conditions, it is in psi, so I should be able to solve the problem, right? What is stopping us from solving the problem? What's the challenging part now? So I have the governing equation and I have the boundary conditions. You still have two variables, right? You have r and theta, right? So you have a partial differential equation still. And that's where the transformation comes in, that partial differential equation is harder to solve. And this is very common, is that to look at far away condition and try to see a pattern, which is very easy in this case if you see, is that del psi by del r is u sine theta, essentially negative sign cancels out. So if I want to find think of psi, it will be u sine theta r. Right? That's why when I differentiate it, I'll get u sine theta. And on the top, if I do differentiate u sine theta r, and you do del psi by del theta, then you will get u cos theta, right? And then 1 by r cancels out the r. So this both implies that psi as r going to infinity comma theta is u sine theta r. Okay. And because we have now we have a PDE, so our PDA is del square psi is equal to 0, which implies that del square psi, let me make sure I get the equation right. It is 1 by r del by del r, 1 by r del by del r of r del psi by del r plus 1 by r square del square psi by del theta square is equal to 0. Okay, this is the equation I want to solve. My boundary conditions are del psi by del theta at r equal to capital R is 0, and that psi as r going to infinity is u sine theta r. Okay. Any questions here? Please let me know any questions, anything that's confusing. Yes.
What table would you find to get what
The Laplace, you mean? Yeah, so I don't know the table number. I think it's table, it should be in the same one here. Let me do, hopefully I get the number right. It should be in A3, A2, A3, A4. Sure, yeah, that's fine. Yeah, I generally post all the slides, so you should have the tables. Yeah. So table A2, A3, A4. So when I post the slides tomorrow, I'll have you should have all the information. Yeah. Table A2, A3, A4. Okay. A2, A3, A4. You can check this. I believe it should be this one only. Okay. So you get this. Yes, please. You mean from, yeah, sure. So you're saying here, from here to here, right? Like this to this step, right? Yeah. So what I'm saying is, as you can see, if you del psi by del r going to infinity is u sine theta, right? And then basically what I'm saying is psi, if you integrate this, you will get u sine theta r, right? And if you integrate this equation as well, you will also get in theta, you'll also still get u sine theta r. So that's it. Yeah. Yeah. Yes.
In some sense, don't we have like plus function?
Yeah, that's a great question. But remember that you will have, if the great question, but if the integrations weren't coming out to the same, then that can be a function of, so if you integrate the top equation, you have a function of r. If you're integrating the bottom one, you have a function of theta. But you cannot have both, right? Because if they're coming out to be the same, that means those both functions have to be 0. So that's why you have two equations, still one answer. Great question. That's a small detail. Yes.
I just have one question.
Sure.
What happens to the integration function?
Yeah, so that was the question that Jason was also asking. So both of you are asking the right question. Let's say I'll just make it c theta, and then if you do this from the other side, you will get psi is equal to u sine theta r plus d of, let's say, r, right? But for them to be same, they have to cross out. So that's why like there cannot be anything spilled over. Make sense? Anything confusing? All right. So this is essentially what you get. I would say just don't get confused by this. You send it to R, and at this point is the point. So this is the point we have gone from psi. We converted the velocity into condition into psi. Combine the two at the partial to get this kind of result. And now it's still a partial differential equation, and that's where your final equation comes in handy here. Is that you will say, well, I look at my boundary conditions, they are in R, right? My boundary conditions are not in theta. My boundary conditions are in R. They are the surface at the cylindrical surface or far away. So I should I am trying to evaluate a function of R, and I see a dependence in terms of sine theta here. So I'll propose a form. It's not something that you can propose a form. The psi is f of R times sine of theta. Okay. And it's very easy, like once you see that you already have at infinity, just kind of make it f of R times sine of theta, because the boundary conditions are in R. So if you propose this form and substitute, you get out, and the sine theta gets cancelled. So the equation basically sine theta goes away. And you get a negative sign, because when you differentiate with sine theta, you get minus cos theta. When you differentiate again, then you get sine theta. So sine theta drops out, and you get one equation finally in terms of 1 by r df by dr, del f by del r, df by dr minus f by r square. And what are your boundary conditions? Del psi by del theta is what? If I differentiate this by del psi by del theta, I get fr cos theta. So that means fr has to be 0, right? So this means f of r has to be 0, and that f of r going to infinity is u r, right? But you also have to modify your boundary conditions. Any questions here? Yes.
So we look at idea of what a solution might look like, but plug that in to form what our actual possible solution is. Right? And then we should go about possible.
Absolutely. Yeah. And if the sine theta, let's say you have bad guess, or you just couldn't, then the sine theta would be spilled over in that equation, the black equation where we have the here where we are. Then I will not be able to. I need an ODE basically. So if my form proposition is incorrect, I will just not be able to write an ODE. That's the whole idea. You now get an ODE, and you have the boundary condition, so you get this. Yes. Yes. So what I'm saying is, note that this is my boundary condition. So del psi by del r is del by del theta of fr sine theta, right? So that means it's fr cos theta, right? And then cos theta cannot be 0 always because it's a variable. So f of r has to be 0, right?
And the one under is u times r? Or
Yes, u times r, because the sine theta is here. So u times r. Yes, absolutely. Other questions here? Okay, so you'll do the exact same thing in your homework, just it will be for a spherical geometry. Just follow the steps, we get to this point. Okay. Now the whole point is just to solve this, and there's not a very difficult equation to solve. You basically plug like you do generally. You will just say f is of the form r is power of n, and just out of interest of time, I don't want to take too much time just to do this. You will get out to be n square minus 1 is equal to 0, which implies that n is equal to plus minus 1. And finally, you will get f as ar plus b by r. You use boundary conditions. Use boundary conditions, and then you will get f as u r times small r by capital R minus capital R by small. Let me check if this answer is correct. Right. So this is what you get out. Okay. So this is just like 5 or 10 minutes of math. Just get this expression out and you plug in the boundary conditions and you get this. Okay. Yes.
Are there any problems we can get imaginary roots to add?
Yeah, it is possible, but not like generally the problems we will give in this class. You could not get that. Probably possible. In which case, essentially, you may not, basically, there is no physical solution. So let's say we imagine a flow problem that we think will have a solution, but doesn't really have a solution, or it doesn't, converge or something like that. It's possible. I don't think you will get that in the problem, but it's probably possible. I'm not 100% sure, but that's my guess. All right, so you get this, and then you get psi. So psi is FR sine theta. So psi is UR sine theta, R by capital R, this capital R by small r. And now finally, I know my VR and V theta. The proposition was VR was 1 by R del psi by del theta. And so 1 by R del psi by del theta is UR cos theta. And what you will get is 1 minus, let me make sure I get you the right. VR will be 1 minus R by R whole square. And B theta is minus del psi by del R. And that comes to be U sine theta 1 plus R by R whole square. Is there a negative sign I'm missing? Yes, there's a negative sign here. Okay, so this is what you get. Any questions at this point? So anything at the process, the whole process, this is exactly what you will follow in your homework to get V R and V theta in that, but in spherical coordinates. Yes, question? All right, so one thing to check here, if you put small r as capital R, VR goes to 0, right? So no penetration applies. And when I put small r is equal to capital R at V theta, do I get 0? When I put small r is equal to capital R, no, it gets 2u sine theta, right? There is a slip. So velocity in the theta direction at the surface is non-zero. So the solution gives you a slip, which makes sense because it's an inviscid flow. And this is a very crucial point. Okay, so you get VR and V theta. And now once you have VR and V theta, what's the second step? Is to use Bernoulli's to calculate pressure. Okay, so use Bernoulli's to calculate pressure. So use Bernoulli's to calculate pressure. And there is ignore gravity, so we are not working with gravity. So our equation is P by rho plus V square by 2 is equal to a constant, right? So I will write this P by rho plus V square by 2 at R going to infinity. And then I'll write P by rho plus V square by 2 at R going to surface. You don't have to do this, but I'm doing only at the surface. You can write for a general R because I'm interested in calculating the pressure at the surface, but you can also find for a general R. Okay. By the way, the solution is just, I'm trying to be specific here, but you can also write P as a function, P on like any arbitrary radius. Because the solution is work and because your velocities, you know that all the radii values, so you can actually find pressure which is general. But I'm finding at the surface just for simplicity. Okay. Just want to identify that this is a solution. Okay. So what's pressure far away? 0. Okay, so this goes to be 0. What's the velocity far away? U, right? So it's U square by 2. The pressure at the surface I want to calculate, and then rho. And what is the velocity at the surface? The velocity VR we know is 0, right? and v theta, I was just mentioning, if you put it, it becomes to be minus 2u sine theta. You can check, you can just put the value here, put small r is equal to capital R, you will get 2u sine theta, minus 2u sine theta, okay? So that means this becomes u square by 2 times 4 sine theta, sorry, 5 sine square theta, and that means that p of r comma theta is rho u square by 2 this is my pressure. Any questions? Anything that's confusing here? Right? So the process, get the first choose psi or phi equation, define the velocities, then write the boundary conditions in terms of velocities, convert them into psi or phi, then propose a solution to write an ordinary differential equation, solve it, then calculate velocity, and then finally calculate pressure given Bernoulli's. Okay. And the last step is to calculate the drag, and that's why I just found it at the surface, because at the surface we can use the pressure. So to calculate drag, and by the way, I want to show this calculation once because I want to make sure that you all are now very comfortable with this. So it's stress vector ds. And stress vector is n dot sigma. Remember that n dot sigma is n dot minus p identity plus tau. Tau is 0 because there is no viscosity. So what you really get is simply, if you do this in this, you will get minus p and ds. Nothing, it's not really, it's very simple. Simply p and ds is your entire force. Okay. So what is my normal? Yes. Yeah. Okay. What's the normal vector here at the surface? ER. Very good. And the pressure at the surface is the pressure written above. So I'm saying it's minus P, which is rho u square by 2, 1 minus 4 sine square theta ER. Okay. And then I still have a ds. So ds, again, please don't worry about like knowing these things, just look it up in the table. ds is, and I'll just, hopefully everybody has written this. So 1 minus 4 sine square theta ER ds. And for ds, we will go to the table. I should have it here. Yes. So we are normal to the R. So this is this one, right? And so I will have small r is capital R at the surface. So R d theta dz. Is there any z dependence? No, right? So it's simply length. So R times L and B. So basically, I'll just write this. So A.734. This is R d theta dz, which really becomes R L d theta. So I'll just go on the other side. So this becomes minus 0 to 2 pi rho u square R L by 2, 1 minus 4 sine square theta ER d theta. Okay. So are we done? Should we just integrate it and get the answer? Okay. Don't forget, this is not at point we cannot integrate yet because we have ER. You cannot, ER is changing its direction continuously, so you cannot add vectors when they're changing its direction, they're changing their direction. So you have to break it into EX and EY, and if you do the answer now, you'll get the wrong answer. So now you just break it into E. So again, go back to the table. It says ER is cos theta EX plus sine theta EY plus sine theta EY. And if you do that, substitute it and integrate, what you will get is drag force is amazingly 0. And for I think almost a century or something like that, This was sort of an unsolved mystery. It's called D'Alembert's paradox. And this is what you also show in your homework with a spherical flow. This drag force is zero. I mean, it's weird, right? You're flowing something at so high a Reynolds number, but the drag force is zero. There's nothing that you calculate. And so fluid mechanics, theoretical fluid mechanics scientists were not considered to be very smart because this was always zero and they were like, you are just doing, I mean, this is obviously wrong, right? And you have done so much math to get to this answer, which is wrong. So yes, Noel, there's a question. Yeah, so that's the point. So it was not very clear first. Why is it wrong? So that's the next question, and that is what we'll discuss. Why do you think this is wrong?
Well, it seems that the fluid like flows perfectly over, so you get like pressure, like what you get over integrating half of it, same, the opposite of the other half. So it assumes that the fluid flows perfectly over it, but really you're probably going to get some kind of separation of that layer, right?
Yeah, so I think you're maybe right. So that's something maybe this is like a concept that we haven't discussed, but I'm saying think about in terms of concept we have already discussed. So you're right. So what you're saying is right, but I'm saying you already know the outcome, so that's why you're saying this is incorrect. But what I'm saying is, why do you think this is incorrect? Like with the concepts you have only discussed, no separation or anything like that.
It's caused by friction. Friction, perfectly frictions flow.
Right, great. So everybody has got. So the idea is we have assumed viscosity to be exactly zero. And there is a difference between the viscosity being small or being exactly zero, and there is no fluid in the world which is exactly zero viscosity. And because viscosity is always finite, and when there is a finite, there is always a region near the surface where there is no slip. And because we do not apply no slip, and slip causes all the change, and that's called the boundary layer, right? Where you have viscous stresses always being important. And that's the portion of our next part of the course, where we go into boundary layers, momentum boundary layer, heat transfer boundary layer, thermal boundary layer. So that is what we'll discuss the next time. But that's why this is wrong, is because viscosity is assumed to be exactly zero. It's never exactly zero. It is small. So Reynolds number infinity is not a number. When we calculate for a car, it was 10 to the 6. 10 to the 6 is not infinity. That means viscosity is small, or like the viscous stresses are small, they're not zero. So that small factor changes everything. And we'll discuss, and this solution, by the way, is still valid, but it's just valid outside the boundary layer. So we'll discuss some of these things in the next part of the course. So with that, we have kind of wrapped up the part 2 of the course, which is essentially fluid flow, deriving Riemann equation boundary conditions, very different kinds of flows, ending with this sort of D'Alembert's paradox. Do you have a question? Yeah.
Like, why is that wrong? I don't know if you already mentioned this, how to choose whether we use star or.
Oh, either is fine. So I would just say, in my view, it's just sometimes easier to use phi in these problems because phi just has a gradient, so you can use in any geometry. Psi, you have to stick to the table, which is the only this case. So phi can actually be in 3-dimensional flow as well, but it shouldn't matter, and we will obviously in any exam will not ask you to derive all of this. So I would say, but in your research problem, if you ever encounter a problem, I would say go with phi because it's just less restrictive. Okay, psi is more common in creeping flows because remember in creeping flows we had a del 4 psi or a E4 psi equal to 0. So there we did not have any potential flow equation, right? So psi is, that's why it's an important concept. But I would say in inviscid flows, potential flow just works just fine because it's more general. Yes.
Will you maybe advise us on a test problem which option to use?
Yes. We'll give you. So we are not going to trick you. Okay, do the hardware or anything. We'll tell you what to do, but you should obviously be able to understand what Let's say if we give you a potential function, how to calculate velocity, or if we give you like velocity, how to calculate pressure or integrate it. So yeah, you're not going to be just find velocities. We'll walk you through the steps in the exam as well. Okay. So let's take a 5-minute break. Let's come back at 12:56, and then I will review the material that we have discussed in this part of the class. And then, of course, I'll have office hours. Okay. All right. I think there was a question, sorry, you got a question, right? Can you please answer this question? There are questions to ask you. So maybe a slightly more newer part is that we ask them actually. So let's say get the numbers right. So let's say you have and then you have 1 millimeter and the length by length by not including our half. So 6,000 more. And that amount is outside that actually. This works. So they look at the last value it's 2 and 1 so that's what we discussed. And I'm going to show the basic idea of this is valid. Just as we get very clear, because bounded condition is correct, and that makes the overlap right. So there are multiple concepts of cognitive. In this case, we will not have we have cognitive so that's where we are how the pressure drop is affected. But this solution works essentially let's say the calculus right around let's say that outside all business when you get any other circuit so that's where it works just not yeah and then this part of it is all really All right, so let's get started. We'll discuss the review now. So review for exam 2. Review for exam 2, and let's get started. And feel free to let me know if there is a concept that's not clear or is confusing. So we started talking about in this as a stress tensor. We discussed that we have we have 9 components in a stress. And in this, let's say if I have a sigma, not this one, let's say if I have a sigma xy, then x is the direction of the normal, and y is the direction of the force. So we define essentially a stress tensor in fluids. This was the first key property we defined, that there is a tensor now because fluid will apply a stress on a plane, and I need to understand what is the direction of the plane, and I need to understand the direction of the force. So the second part was, if we know the plane, then how do I calculate force by the fluid on the plane? And this n basically points into the fluid, and this is stress tensor, and this is stress vector, right? So we discussed this. The key property for calculation of force is stress vector, and force is essentially S and ds. Okay, S and ds. Remember that n points into the fluid, and then you can calculate force. As you can see, I hope as you have seen in this entire part, that force calculation is one of the key components that differentiates this part from part 1, because we at the end always try to calculate drag, try to calculate force, calculate torque, which you're doing in problem 3. So basically that is a key component that differentiates. And whenever you're integrating, please make sure that you're always decomposing in Cartesian coordinates, decomposing in Ex, Ey, Ez. You cannot solve the problem we cannot integrate forces in E theta, Er, or E phi. Okay, so that's not allowed because the vectors are changing, and that's why you go to static coordinate system when the vectors are constant, so that you can sum the values in each direction. All right. So that was basically what we have. That was the fundamentals. Then we derive the boundary conditions. Governing equation first. Governing equation. And we derive the Navier-Stokes equation, and for constant density and constant rho and mu, we use the equations rho del v by del t plus v dot del v minus grad p plus mu del square v plus rho g. Okay, and the entire challenge, that the whole part 2 was because till date we don't have a general solution for this problem. If you have a general solution, you don't have to worry about lubrication, inviscid flow. It's all because these equations are very highly nonlinear, complex, so that's why we cannot solve them directly. Okay, yes.
For the exam, we have to know, in part 1 of the course, we had like an equation for like the normal vector and a line for the unit vector.
Right. Yeah, so we also had it for part 2, right? When we had like a ball bearing problem. Yeah, so I think that's something you should know for the exam. Yeah, we'll discuss it. I'll come to the ball bearing problem and discuss it.
We practice you like
Not for this. So we'll always make sure you always use this. Okay. I mean, it's good to be aware of that for a research problem, but for the purpose of this course, we'll not go beyond this assumption. Okay, that's something that we'll not attempt to ask. Yeah, again, no trick questions. Okay. We'll stick to what we have discussed in class. Any other questions? Okay, this is what we will do, and then we'll have the second part was the boundary conditions. And that remember that when we have a fluid solid interface, then we will say we have either no slip, no penetration when the stationary, sorry, stationary, yeah, stationary. But if it is moving, then we had a U and we had a V naught. This was for porous. This is your air hockey problem, a slip. This is something you did in your homework 3, where a plane was slipping. So, parallel movement. So hopefully these boundary conditions are now becoming very familiar. And now you have seen several examples as well of when you apply, how you apply these boundary conditions. Okay. This is for fluid solid. If we have liquid fluid, but we have fluid with no velocity. So it could be liquid, it could be liquid air in this case. The velocity has to be 0 or hydrostatic. Hydrostatic. And so here the boundary condition is P1 minus P2 plus 2H gamma is equal to 0. And remember the normal vector goes from one interface 1 to interface 2. Okay. So P1 minus P2 plus 2H gamma is equal to 0. Felipe has a very nice video on the supplementary video which tries to tell you the sign of this equation curvature. So I highly recommend that. It's confusing. And I have always been confused, and we basically have clarified for the first time in the course how to make sure this actually is consistent. So it is consistent where H is the mean curvature. Okay. This is mean curvature. And this gamma is the surface tension. And for this portion specifically, I would say, remember your homework 3, problem 2, and homework 3, problem 3. Okay. So this is boundary condition you apply for hydrostatic problems, buoyancy, which you calculate on a sphere and showed how the Archimedes principle works. And then problem 3, you derived an equation for the shape of a liquid up near the wall, the contact angle. You didn't solve it, but you kind of got a sense of how to use this boundary condition. Okay, so that was the purpose of homework 3 on kind of focusing on hydrostatics. Then, if we have a liquid air interface, then we assume viscosity is 0. Sorry, in the air phase, mu air, and then basically becomes Vn is equal to 0. There is no penetration, and tau RT is equal to 0. Sorry, tau NT is equal to 0. Tau NT is equal to 0. Okay, so note that there is no slip here. No slip. So no slip is not valid in this case. Or many students apply that by mistake. Sorry, let me just push this up. No slip is not applied in that case, so you use that. And where are you using this? I hope some of you have done this now. Problem 4, right? Where you have the bubble problem. You cannot apply no slip, so you apply tau NT, and that changes the entire structure of the problem. Okay? So always remember, we cannot apply this problem. And in one of the conceptual questions also, we will give you a similar problem. Or like a conceptual question, not like a boundary condition question. How to think of a boundary condition. Any other questions for this boundary condition or anything like that here? Everything is clear?
There's no shear stress because the air
Because the air has a 0 viscosity. So air can move, but it never exert stress. So let's think of it like this. Let's say if I'm flowing something here, right? Let's say on this desk, if I'm flowing something, then if open channel, and air here, air can move, but it will not exert any stress. When I'm balancing the force, then I cannot have any force. And no force means that I will not have any stress. In the parallel direction. So that's why note that's why you have a T here. Because that is the direction of the force. And N is obviously the surface. So that's why tau and T is. By the way, I forgot to mention one thing, just a small point here that we discussed that sigma is minus pi plus tau. Minus pi plus tau. All right. All good? All right. So then we start discussing hydrostatics first. Hydrostatics. The model problems we discussed in class were, how if we have like a fluid here, and we discussed how we had a block, and we discussed forces on each of the faces. So basically what you in hydrostatics, and there the other problem was this contact angle problem. Okay. And these are the two model problems I will say you should understand. The main idea is to understand here that generally we think of z, x, and so on, that pressure is only a function of z, right? And that when you apply, you take the normals here, pointing into the fluid phase, and so on. And that's how you typically calculate all the forces. Okay, so just understanding how to calculate forces on each surface and how to calculate pressure is only a function of z, and then applying this boundary condition, which I was mentioning. In this case, you apply this P1 minus P2 is to which gamma is equal to 0 to get to the right answer. Okay. So just kind of understanding the concepts here, and the basic equation here is only simply minus grad P plus rho G is equal to 0. There is no flow, so our problem is much easier. So it's just a simple equation. This is a government equation. This is a bit fuzzy here. Okay. Any questions? All right. Then we thought about, we said, okay, the next is unidirectional flow. So model problem is, I would say, the one that you did in your homework, which is a view P1, P2, and you had like sort of something like this, or maybe I'm getting the velocity profile wrong, but I hope you can kind of, there was a superposition of this plus a velocity profile that goes like this. Right. So linear plus a quadratic, which you did in your homework, and then you can change the pressure gradient and velocity directions to kind of superpose that. And this is a good problem. And remember that in this case, Vx is only a function of y, and dp by dx is equal to constant, and Vy is exactly equal to 0. Okay. So this is a good model problem in directional flow. The other kind of unidirectional flow is actually the rotational flow that you're currently doing in your homework. And so I'll just make that as a case here. So basically remember that you can also have where basically V theta is only not equal to 0, VR is equal to Vz is equal to 0. Okay. So that's also possible. So these are the two problems I would say. If you're thinking about it, these are a good kind of way to remember how unidirectional flow problems are solved. Naturally, this is more complicated. The other one is a little simpler, but this also involves, on top of force, also has torque. So good way to think about torque and so on. Okay. All right. Any questions here? Anything that's confusing? All right. So then we had nearly unidirectional flow, and I should mention, for the purposes of your exam, understanding nearly unidirectional flows and lubrication is probably the most important, as you can imagine. Those are more advanced concepts in terms of the long problem, nearly unidirectional flow. So here we discussed this case of h of x here, and this was 2h. It was a linear problem in this case, and we had we basically have Vx is a function of x and y, Vy is a function of x and y, P is only a function of x, and Vy by Vx is much smaller than 1. So I think this is probably the longest part, this and lubrication. So this is a good problem to remember. The other problem we discussed is the ball bearing one, right? And in that case, the normal vector was here. So now I will discuss the question about that this was y equal to h of x. We had x and y. So to find the function, we said it is y minus h of x. And to find the normal, you take a grad f by mod of grad f. And that is ey minus dh, and is the plus minus here. Okay. And he said we'll choose the minus sign because then it has to point here, opposite into the fluid. So this was a shape factor coming into the normal. Okay, so like maybe I can take a question. So what was the confusion in this step? Maybe there was a, so basically when you get a function here, you define a dummy function like a y minus h of x, take a gradient, and then make sure that it points into the fluid. So for an exam, for instance, what could be a potential question is, we might ask you to basically figure out the right normal direction or find a force using that normal direction. So, generally students get the direction wrong or some steps become. But generally the idea is to make sure you remember to point normal into the fluid. That's the key part. And if you know the shape, you just basically write a shape function like y minus h of x and take a gradient. Yes. Yeah, so good question. Yes, absolutely. I would say not necessarily on the governing equation, but make sure to practice what are pressures, tau xx, tau xy, and so on. So make sure to practice this and force, how to calculate force and so on. So scaling analysis is absolutely very important. It's probably very, very important for the exam, and just in general understanding this as well, how to get everything correctly scaled. Okay, so make sure to practice that. So to give you an idea, the air hockey problem is there also. You can practice, and you're doing this anyways, but maybe when you're trying to revise your for exam, maybe you can also try to do an order of magnitude analysis on pressure, velocities, and so on, right? VR, VZ, and so on. So like try to learn to sort of look at the equation. No? So before I jump ahead, remember that we use the dp by dx is equal to mu del square Vx by del y square. This is the primary direction, primary velocity. And this is the thin direction. This is how we write the equation. So you are not expected to derive this equation. You can just directly write it in an exam. Okay, as soon as you know the yes. Not always. So I think this was a question that I got a few times. So maybe let me just clarify. Not always. So let's go to the. I hope I have the Navier-Stokes equation here somewhere. I do have it. So, okay, so let's go to the cylindrical coordinates. Okay, cylindrical coordinates. Now, let's say you have, you are told that your z component is the dominant velocity. Okay, z component is the dominant velocity, and r component is the small component. Okay, so r component is the small component. In that case, as you can imagine, for instance, here, my z component is the dominant velocity. So I will look at the z component. But the derivatives I need are the r. So this will be the term that we carry. Right? Because so it doesn't basically, the derivative doesn't have to be del square Vx by del y square always. It is the term which is kind of as a primary component of the velocity with the smaller component which we carry. Make sense?
Yeah. Last class when you were talking
The disk problem, right?
I mean, the air hockey thing.
Yeah, right.
You wrote like,
Yes, because that's the r component of the velocity is dominant. So and the derivative of r with the z1 is normally del square vr by del z square. So yeah, this has to still hold. Just that which component? So is everybody seeing that? That let me put the arrow here. This is the term that stays over for the air hockey problem, because VR is dominant with the derivative with the z. But in the cylindrical problem, which is the first problem of your homework, where you have the sinusoidal variation, you have this problem holding up because it's the z component of the velocity with the r derivatives. So you cannot just write del square Vz by del r square because then you're ignoring the curvature. But here it doesn't matter because it ends up being the same, just because it is like this is the scenario. So yeah, just remember that when I write it in the lubrication, this is just a representation. This does come from finally simplifying this equation. So you'll only have the terms which are, the larger velocity and the small. Okay. Yeah, so I will post the entire slide deck from here, like from this lecture 11 to 19. So you'll have all of these. Yeah, I'll make sure to do that. And so any other questions here? Because lubrication is very important, so I want to make sure you remember that. And then invariant, so invariant could be Q, small q, capital Q, or V naught like air hockey. So this is already you have an idea of how to think about it. Okay. So just so that I close all the discussion here. So once we discussed all of this, then we discussed the lubrication, the creeping flow, right? So creeping flow, there are essentially two problems that you can focus on. Creeping flow, you have two problems that you can focus on, and that is the squeeze flow problem. So we had the velocities going this way or this way, and this was u of t and u of t, and the flow was getting squeezed out from this side. And so remember that in this problem, the main point was that this is a time dependent boundary condition. So because Reynolds number was small, we could make it a pseudo steady problem. So it was a lubrication problem made pseudo steady by the low Reynolds number. So that's why like this, the equation will still hold. This equation will still apply here, but we can still use a time dependent boundary condition because the lubrication was derived for a steady system. Okay, so it's kind of like almost like a similar idea. And then here also you have, force balance. So remember that what is the order of magnitude analysis or scaling analysis plus, force balance, I would say is very important here. And for this, please make sure you can refer to the supplementary video, which goes through all the calculations so that you can make sure that a force balance is clear. Okay, please make sure you remember that. Felipe also has a nice, interactive simulation if you want to take a look, in which case we basically added a pressure gradient on top of this. So basically the streamlines were not symmetric. There was some sort of asymmetry coming in. So it's a very nice simulation to kind of just for your understanding. You don't have to like do much about it, but just for understanding what is going to happen in the system. Okay. And the second problem in creeping flow is the flow passer drag calculation. So I think it was, I'll write it like the homework as well. So like this, which is what you are doing in your, this is your homework 4 problem 4 and your, and the Stokes drag. So that's the key part here. So just learning how to kind of, you obviously we will not give you that derivation, but we may ask you for a step from one of the derivation to make sure that you understand like how to go from one step to the other step, or like something like a terminal velocity conceptual question, which we had in the class, like are you double counting the force and so on, or a force balance. So that those are the kinds of questions we typically like ask in this. And remember that the governing equations are del force psi or E force psi is equal to 0. Okay. So that's how we solve the problem. Okay. And then finally, the only part that I have not discussed is the inviscid flow, where so I'll just complete it for the sake of it. Inviscid flow. So it's del square phi is equal to 0, or del square psi is equal to 0, or E square psi if you have a different geometry. This is table 612. And this is basically table A2, A3, A4. And then you have the P by rho plus V square by 2 plus GH is equal to constant. This is what is the inviscid flow. Okay. So note that in all the cases, note how governing equations change, right? So this is del 4 psi or E 4 psi is 0, del square phi or E 4 psi or E square, del square psi or E square psi is equal to 0. Inviscid flow. Then you have this primary direction and the smaller thin direction in the lubrication flow or the squeeze flow problem. And then when you had initially here for the rotational flow, we just start from the original equation unidirectional and just drop off all the terms, right? And then before that, for hydrostatics, you just had minus gravity plus rho g. So essentially, we are always using the same equation point, which is a Navier-Stokes equation, but we're just modifying them. For hydrostatics, no velocity, then dropping all the terms systematically for unidirectional flows. For near unidirectional flow, using this primary direction approximation, then del 4 psi or E 4 psi, or to finally del square psi or E square psi. Okay, so that's essentially the whole spectrum of different kinds of flow problems that kind of are primarily used in mechanics. I will now have my office hours. I think that's hopefully enough for review. And then I will have the office hours on Sunday as well. And we'll post all the practice material, including all the slides, questions tomorrow morning, so that you'll have everything once your homework is done. Okay. All right.